Thank you for having me to the conference. My name is Dr. Cheng. My co-author, Dr. Simon C. We are going to present topics on partial problem-based learnings using the open source of acoustic software educations for marine engineering degree programs. Introductions. Vessel has facilities for housing the workforce for the entire voyage at seas. Recently, offshore vessel and hotel offer alternate solutions to house workforce personnel. As you can see from these diagrams, so the concept of crew habitability has assumed far greater importance in maritime and offshore activities in the recent years. Ship owners are looking to limit noise as much as possible nowadays. The workers on the offshore platforms are often subjected to very high noise levels while working in the enclosed machinery compartments such as engine rooms. The traditional way of predicting the noise in enclosures, mainly using the commercial software to compute sound pressure levels, which is quite expensive. So we need to avoid costly retrofittings in the later implementation stage. That's the main reason that we want to use the software. And for different classification society, the maximum allowable SPL of 60 dB is also agreed with the ship vibrations and noise guideline by the Society of Naval Architects and Marine Engineers, known as NAME. In addition to the SPLs, main parameters of metrics for sound qualities are the psychoacoustic properties related to human perception of sounds. They are namely loudness, sharpness, fluctuation, strength, and roughness. In marine industry, some of the workers become hearing impaired after long exposure to noise or due to the work-related accidents. So it's very interesting to expose the student to different calculations for special needs workers in their workplace. So hence it become quite important to include the following topics in my studies. So the study of the room acoustic in the marine engineering is still lacking in the literatures. As you can see, most of us are using the traditional kind of teachings. Hence, the problem-based learning methods seems to fit the requirement for room acoustics in the marine engineering courses. Although the concept in acoustics do not change much, applying human perception in room acoustics is important, where the crew members are often confined in the offshore environments for a long period of times. So the traditional learning, as you know, is we are told what we need to do. We memorize it and problem assign to illustrate how to use it, often through tutorials. But for problem-based learnings, we often have the problem being assigned. We need to identify what we need to know, and then we learn and apply to solve the problems. So the exposure to soundscape onshore can be different as there are fewer moving vehicles, buildings, and pedestrians as compared to offshores. And also there's more machineries and equipment surrounding the compartment where the crew members are staying. So instead of full PBL implementations, due to the time limitations, partial PBLs involving just the problem definitions, discovery journals, group representations, and report will be used. So in summary, this study aims to conduct acoustic analysis of the room model by investigating the SPL, reverberation times, and the response of the acoustic parameters via partial-based problem-based learning methods. So for the course curriculums for partial problem-based learning, as you can see, it's a 3 years marine engineering degree program by Newcastle University in Singapore, and the duration is 12 weeks. To complete the modules, the students must substantiate the learning through a group project in the second weeks, and the instructor will review the acoustic topics to equip the student with some fundamental before they start these partial problem-based learnings. And for grouping wise, we should not allow more than 5 students per groups. So you can see that the PBL activities includes the problem statements, discovery journal, problem project reports and presentations, project feedback. So the weightage you can see from the right hand side of these tables is 20, 40, 30, and 10 respectively. For the course curriculum for partial based learnings, I just want to explain a bit more on what is actually the problem statements. This basically enables students to identify and understand the problems. And also the discovery journals will involve the literature review on various methods to compute the sound pressure level, reverberation times in the room, and the sound quality of the room, such as the sharpness, roughness, and etc. The following tasks will be performed by the students. First, they will use the Pi Sound Tree, which is a MATLAB software to determine the sound pressure level for rooms. And then you will be using the again the MATLAB by using the AARAE to determine the reverberation times for the room acoustics. So there's two software that they will be using, and this is just the illustration of the snapshot of how this open source MATLAB software look like. So this is the first software that I mentioned using the Pi Sound Tree, and the second software is basically audio and acoustical response analysis environment results. And then we will have to do that, let's look at the result and discussion of the PBL approach. As we mentioned, the MATLAB packages are used to compute the sound pressure level, reverberation time, and as well as the psychoacoustic parameters for rooms. And then the student will conduct a correlation studies between the psychoacoustics and the sound pressure level using the Minitab software, which is basically a statistical software which we need to use to conduct the correlation studies. So this is the picture of how the room will look like with the dimensions, and the property of the tables basically will be the room dimensions, the frequency of interest, which is basically the very low frequencies, and also the pressures, distance to the noise source, and so on. And the material and absorption coefficients for the room models can be seen here. Because there's 6 sides for the rooms, and each materials or each wall is made of slightly different type of materials, and the absorption coefficient has been used, as you can see from this table. The result and discussions to carry on with that, the sound pressure level was measured using the handheld ATTAC HD600 sound level meters, and there's a condenser microphone here, and it's manufactured in line with the NSI and IEC 61672-1 Type 2 standards. So the measurement is recorded at least 1.2 meters from the wall, and the room is quite small, so the measurements were performed in the center of the rooms. So if we collect using this measurements device, and we base on the average value of 46.9 dBs for 65 seconds we have recorded with a total of 131 data points. So the sound pressure level is 46.9 dBs for the rooms. And for the reverberation times, we base on the -5 to -35 dB part of the sound decay. Alright, so you can see that we are actually using the 4296 BNK omnidirectional sound power source with a pin noise test signals. And the result for the two source receiver combination gave us the spatial average value of the rooms, and the decay was measured over the 30 dB drops and then extrapolate to the 60 dBs. And as a result, okay, this is basically the setup that you can see here, and we actually borrow it from the vendors. And the result give reverberation times of 0.78 seconds. So with that, we compare this experimental, as I mentioned, that we collected from the device that we used to measure the room, SPL, and we compare with a different type of model in the literatures, which is mainly the empirical approach. So there's Thomson, the Kaftroff, Snames, the Hirama, and Hossens, and Surya. So these are all the sound pressure level that we obtain, that we use the models and try to numerically calculate the results and compare with the experimental results. And as for discussion of all the results for sound pressure levels, the Sname methods has the highest value of 55.4 dB with a difference of 18% against the experimental results. The environment was in the ship compartment ranging from living quarters to machinery rooms. So the ship has many confined compartments containing different machineries and equipment installed. So having the system operate at prolonged hours, noise can be presented throughout the days. And we also look at the serial model has a difference of 10% against the experimental results, which is less than the SNAME methods. As for the reverberation time models, again, this is the experimental result in red color, and the rest, as you can see from the left hand side, is all the empirical approach that we extracted from the literatures. So there's a few methods which we label as the T1, T2 to T7s. One of the traditional methods is Sabin, which is the typically we use for measuring we use to compute the reverberation time model. And the classical Sabin formulas reasonably predicts the rooms with around 1.9% errors as compared to the reverberation times model and the experimental results. But Aaron Puchali model estimates the smallest error of 0.2% as compared to Sabin formulas. And the Sabin correlation models form the fundamental basis of reverberation time using the simple room models, whereas the Arun's methods accounts for the design layouts and energy losses to the surrounding environments. As for the next one will be a psychoacoustics for the room acoustics, and this is the 95% confidence levels of predictor variables that we use: the dynamic loudness, roughness, and the fluctuation strength. And these are coefficients, and this is the 95% confidence intervals. So if you see that the coefficients on the middle of these columns is negative, this means that the response decreases as the term increases, and the narrow difference between the 95% confidence intervals. So it shows a higher precision of dynamics, loudness, which has highest precisions and confidence levels. And the roughness and fluctuation strengths on this test sample has a value of 0 within the confidence levels, which you can see there's a range from -0 to the positive values. And you will find that it's not so significant, and the loudness and dynamic loudness are further than analyzed, okay, for these two parameters. And we also use the regression correlation functions, a possible combination model consisting of loudness and dynamic loudness, and also the combination of both together. And this is the R squares and the press and all these parameters that we use to see whether is it statistically significant. As you know that the p-value must be less than 0.05, and then we can see that the loudness can be predicted with a good accuracies for certain sound pressure level as well as dynamic loudness values. And we also have regression equations to represent the dynamic loudness, and also both of them together using an equations, and this is what we call the regression analysis. And this is some of the equation they want to display and show here. And with that, I could like to conclude this is a partial problem-based learning approach, and the curricular models of the room acoustics was proposed to enhance the student learning in the room acoustic using different open source software package. Thomson model for sound pressure level estimate actually estimate a smallest error when compared to the experimental results. Sabin formulas for reverberation times estimate also produce quite an accurate prediction at just around 1.9% errors when compared to experimental errors or the experimental results. Among these predictors, loudness and dynamic loudness appear to be a main driving force in influencing the sound pressure levels response of the room models. In summary, the students have a better understanding of the room acoustic as a result of using the softwares to predict the sound pressure level, reverberation time, and as well as some of the psychoacoustic parameters. And also try again to appreciate the needs to perform initial design to minimize the high costs incurred in the later implementation stage. So with that, thank you very much.